Hi and hello everyone. What we have seen so far are queuing models or queuing systems which can be modeled by a stochastic process with Poisson process arrivals and exponentially distributed service times and simple variations thereof, right. That is what we have seen. Variations mean we talked about this bulk arrival or bulk service queues that we have, right. So, which we have handled through this Poisson exponential model, basically together if you can call, right. But in any system that if you look at it, especially in practice, like you would see that the exponential distribution assumptions, whether it is for the arrival process or it is for the service process, this may be a limiting the applicability of this particular model, especially the the service time assumptions on exponential distribution, because this Erlang himself have found out, right. It is not just that it is a new thing that it has to be discovered, right. So, especially the service one, like this may be a limitation of this model, if we have to apply this. So, what we do now, like we will try to go beyond systems having this Poisson exponential assumptions. Then if so, then how do we handle such queues where the inter-arrival times and or service time distributions are not exponential? There could be many ways in which they can be handled. What we can look at, for example, one way is to express this distribution in terms of exponentials, right. Whether these distributions can be represented through an exponential distribution. If so, the advantage could be, right, then whatever we have done so far, the approach which we have carried out with respect to the Markovian queues, like they will all still hold good, okay. And such a method, suppose if you can use this idea, like if you can express the given distribution in terms of exponential, then one can use what is called as generally method of stages. Of course, we may not use the terminology, but that's what we are going to do is basically is that, okay. And when you do that, you can still be within the Markovian framework, so our approach will remain the same. If that is not possible, okay, then you can try to handle with the actual distribution itself, if that is amenable in some sense, right. That amenability we will come to that later, which we will also do later. So, that is what is our study of the last portion of this course, which is the MG1 or GM1 models, how one can handle that, okay. But if that G, that your general distribution that if we have, it is too complex and it is not amenable to even that kind of treatment, then one has to use some kind of approximation methods based on the mean and variance, and you may not deal with the distribution itself, but you may be limiting to mean and variance, and this is we are not going to cover in this course. So, this is beyond our scope, right. So, first approach is this one, this is what we thought, right. We are trying to express some sort of a general distribution which is not exponential, but we are trying to express it in terms of exponential, right. So, within that framework, the Erlang distributed inter-arrival or service times form the starting point of dealing with more general distributions, and what kind of distribution that can be handled by this approach is what we will see now. Now, what is this Erlang distribution, or in notation we will be using this E suffix k. What does that mean is as follows, right. Recall that if we have a gamma distribution with parameters alpha and theta, we have assumed a PDF of this form, right, where alpha and theta could be any positive numbers, right, alpha. So, theta to the power alpha by gamma of alpha, this is the gamma function, right, which is what the well known gamma function, right. If it is alpha is integer, then it will be alpha minus 1 factorial, otherwise it is alpha times gamma of alpha n minus 1, and that can iterate to get certain value of that, okay. And t to the power alpha minus 1 and e to the power minus theta t this is what is the PDF, which has mean as alpha by theta and variance of alpha by theta square. Now consider within this gamma distributed random variables a special class of distributions where this alpha parameter, the first parameter alpha is restricted to a positive integer, means it could be alpha could take values either 1, 2, 3 and so on. Okay. Specifically, we take alpha equal to k, that is what we would refer to that as Erlang distribution, but in addition for for certain purpose it will help, which we will just explain. This parameter theta also we make it as if is equal to k mu, it means this k we bring inside this theta parameter also, where k is any arbitrary positive integer and mu is any arbitrary positive, mu is still greater than 0. So, this gives with this alpha equal to k and theta equal to k mu gives the Erlang family of distributions, and then the PDF would then be equal to this, right. I just have to substitute for theta equal to k mu and alpha equal to k, then you will get this expression for the PDF. Now, if you write down the cumulative distribution function or the distribution function of this Erlang random variable, then it will turn out to be this, right, which we have again we have used it right from the MMCK model and other models, like we have used a result which is connecting with the CCDF of the gamma with respect to the Poisson. So, that is from there this comes here, right. You see that that result is we are using it in many places, right. So, this is 1 minus of this probability of x greater than t, right, or t greater than t is what then this quantity is, and obviously like f of t will be equal to 0 for t less than or equal to 0. We are writing it down just for the sake of completeness, otherwise it is clear. Okay. Now, for this form of Erlang, which is what we call Erlang distribution in general, unless we say otherwise, this is what is the form that we will say Erlang. Okay. Now, this one will have mean as 1 by mu, right, variance as 1 by k mu square, right. So, one can easily get the coefficient of variation in terms of only k, you do not need to keep both the parameters in, that is the advantage, and also the mean we are keeping it as 1 by mu, right. So, this the parameter in this thing which is this mu that is occurring here would be the rate of arrival or rate of service or rate of arrival, that would still we want to retain it in that form, and that is why we are making this adjustment to this theta parameter also k. In general, sometimes, right, even if you do not make this kind of adjustment, we can still call it as an Erlang as long as this the alpha parameter is k, which is a positive integer, but we will always keep it in this form unless we say otherwise, right. That is what you keep this in mind. Okay. So, for particular values of k, right, this distribution is what is referred to as Erlang Type K, right. When you say now EK distribution with mean 1 by mu, then you have specified both the parameters of the Erlang, which is k, right, which is coming in this, and mu, which is what is this one. So, this theta parameter would automatically would take the form k mu. So, that is the form that we will be dealing with Erlang, like whenever we are deviating from this particular form of Erlang, and we may not call this k mu. Suppose if you keep this as mu, that can still be called as Erlang, but that then special case of gamma as well. This is also special case of gamma, right. But like whenever we happen that way, like we will mention that, otherwise in general we would take theta to be equal to k mu form is the common form of Erlang, which goes without saying. Okay. But one need not get fixated with this k mu factor alone. So, we need to be liberal on that side. Okay. Right. So, this is what is we define to be Erlang distribution, right. Now, if you look at what else we said that it might give a better fit or whatever, why it can be considered to be more general than exponential. So, here we have plotted the probability density function of an Erlang distribution with simply mean as 4. So 1 by mu, so mu is taken to be 0.25, that is all we have. Okay. And for different case we have plotted the curve. So this blue one is what is k is equal to 1, which if you look at here, if I put k is equal to 1, then what you will end up with is essentially the exponential distribution, right. So this blue line is what is the exponential distribution here. Okay. Now this red one is with respect to k is equal to 2, and this orange one is with respect to k is equal to 5, and this purple one is with respect to k is equal to 10, and this green one is with respect to k is equal to 25, and this blue is k 50, and this dark red is k is equal to 100, right. So as you see, for k is equal to 1, it is in exponential. Now as you increase k, so the Erlang from this light red to this orange or to purple to green, as you see, this distribution becomes more symmetrical and more closely centered around its mean, right. So mean is 4 here. So this is what. So now if I take k is equal to some say 1000 or something, you would see that the curve would still be something like this, it will go, right. So it is more closely centered around its mean, and as k tends to infinity, then this Erlang becomes deterministic with 1 by mu. Okay. So this flexibility in modeling, right. So we have now two parameters as opposed to a single parameter which was there in the exponential. So with this, by playing around with these two parameters, right. So this can model many different distributions which can be of this form. Suppose if it is of say this form, right, suppose, right, then you know that you cannot model this kind of behavior which you have observed through an exponential distribution, but it can be with a Erlang distribution. Or suppose this orange line is what you observe closely when you observe some real system, that this is what is turning out to be from the data, the distribution. Now how do I represent? This cannot be represented through an exponential assumption. So then I have to find a way. So one way is that look for an Erlang distribution. You know the mean, right, here mean is 4, but if this is slightly skewed this side, right. So this is, you have this side is more probability that you have here to the left of this mean is what this orange things would give you, right. Now that would give you like whether for what kind of case that you can get a close approximate distribution which will be mirroring this blue orange color distribution. So it gives more flexibility in fitting the distribution that you observe from the real data than what you could have with respect to an exponential, right. So this is what you are observing here by looking at certain plots of this distribution function. Now like you can see like it can fit with different mu's and different k's, it can fit quite a bit of general distributions can be modeled through this, or at least approximately if not exactly, right. So this Erlang distribution is useful in queuing analysis because of its relationship to the exponential distribution, right. We know from this form itself, right, or when this alpha equal to k, like what would be the, which means when this alpha is an integer parameter, then it can relate, you can relate this distribution of gamma distribution with an integer valued alpha to its exponential, to some exponential distribution, and that relationship is what is be exploited, and this Erlang distribution whenever it is used in the queuing analysis. What is the fact? The fact is the sum of k IID exponential random variables with mean 1 by k mu is an Erlang distribution, right. So what you have here, suppose, so this is what is your scenario. So this is an, each one of them is an exponential with k mu. So, each one of them is an exponential with k mu. So, what you have here, as if some arrival happens here and something moves here, or the distribution, the time, if it is inter-arrival time or service time, this duration, suppose if you think is an inter-arrival time or service time, suppose if you think this service is consisting of some k stages, independent stages, and each of the stage is exponentially distributed with parameter k mu, then this total time can be represented as the sum of this k number of IID exponential with parameter k mu, right. So, that is what is the fact. So, this is what will give you an EK distribution. So, what this gives us is that you can look at these stages as steps, or in general this is what is called as phases. So, this is, suppose if you think of this as service, then as soon as it enter into the service, this is in first phase, second phase and so on into the kth phase. So, but remember there is a only single server, suppose whatever is the server, only one server or two, the server that is handling here, right, would also handle the second phase, would also handle the third phase, would also handle the kth phase before he takes up another customer. That is how this thing will be looked at, right. So, the same service facility is what is this serving different phases. Each of these phases can be considered to be IID exponential with parameter k mu. So, this makes it possible to take advantage of the Markovian property of the exponential, because we know that Erlang distribution by itself is not Markovian, but Erlang distribution, if you view it as if it is a sum of some number of IID exponential, then the properties of this exponential distribution that gave rise to this Markovian property nature or Markovian models can still be exploited to handle this kind of distribution. So, but as you see that this so in that sense, say for example, if there is a some laboratory test is there, so you are getting into that laboratory, there is one technician and then that technician has to perform multiple tests on you, and each of these tests takes an exponential amount of time. See the total service time, unless he finishes with you, he cannot go to the testing the other person, right. Suppose if this is a scenario, so here basically you have naturally you have phases which are exponential, but in many practical applications, right, this may not be the case, but even then the uses of phase helps from a mathematical perspective, because we can then benefit from the properties of the exponential distribution or the Markovian models, right. So, there could be examples where the service consists of steps performed by the same server with each step following an IID exponential, just like we have seen in this laboratory test kind of situation, or even if it is not there, it will be useful to think as if the service consisting of phases. Only thing is the overall distribution should be approximately at least close to some Erlang distribution with for some k and some mu, right. But the drawback that you will be having with that is that as the number of phases increases, the state space of the model, if you have to bring this within the Markovian framework, then the state space of the model would also increase and the model becomes complex to handle it, right. So, there is always a trade off, how much effort you want to put in if you want to bring it under the Markovian ambit. If not, maybe it may be useful to use some other way, directly taking that as a distribution, okay. So, that is what is the plus and minus of viewing this Erlang as a sum of exponential, just to try to take advantage of the properties that the exponential distribution might give you, okay. Now, this idea of phases, right, phases which is of exponentials, to construct distributions, this can be generalized to include a much wider class of distributions than just Erlang, and this particular class of distributions are what are known as phase type distributions. Okay. So, this distribution uses the concept of phases and the distribution that has these properties naturally are Erlang, which we have just seen as a sum of k IID exponential, or hyper exponential, hypo exponential, which otherwise would also be called as generalized Erlang, or Coxian distributions, right, are a much general, even without distribution fitting into these 4 types, a general phase type distributions. We will see how we can describe that. So, this is what we call phase type distributions. And what is the advantage if you want to use the phase type distribution? As we already said that you can still be within the Markovian framework. So, you can use all the theory that you have developed so far into analyzing such models which are given in terms of phase type distribution, whether it is intra-arrival times or service times. Okay. And also the theoretical property that this phase type distribution has as is this class of phase type distributions is dense in the field of all positive value distributions. What does that mean is it can be used to approximate in quite good approximation it can give you for any positive value distributions. Since in queuing systems we deal with only non-negative random variables or positive valued random variables, right, because it is basically whether you are looking at either service time or intra-arrival times, right, this cannot be negative valued, right. So, it is positive valued random variables. Then this any such distribution that you can have with appropriate picking choosing of this k and mu Erlang, or in general even if it is not falling within this Erlang or hyper exponential, hypo exponential or Coxian distributions, then one can use a general phase type distributions, right, to approximate that particular distribution using a phase type distribution. And the phase type distribution is again brings in the concept of phases and phases of exponentials, then the general Markovian theory would apply. So, particularly if you see, if I have a phase type distribution, then I can as well approximate any general distribution that you may have to handle with respect to this a phase type using a phase type distribution. And that is why this popularity of these phase type distributions are there in many of the queuing analysis that one does, which takes you closer to the reality than say an MM1 or a simple exponential model or even Erlang model or anything of that sort. Okay. And since in the last since late 1970s or in the early 80s, in the last 4 decades, you could see like large number of research work has been done on these phase type distributions, their properties, and how they can be applied successfully to queuing theory, to develop queuing models which can model quite good very well the real life distributions that you may encounter in this case. Okay. So, that is what is the advantage of phase type. So, up to this much phase type distributions is what is the generalization that one can make, and you can still be using the Markovian approach, which we can call as Markovian approach, Markovian model approach, and that is the beauty of such wider class of distribution that you can think. Okay. Now, let us see how one can view this Erlang as a phase type distribution in general. So, this is, we have already said that Erlang has a sum of IID exponential, right, but we can also look at the an alternative way, thinking that exponentials arise naturally as holding times of the process in a Markov chain, right. So, if I take a continuous time Markov chain and if I look at the sojourn time or holding time of the process in a particular state, that is exponential. So, I can think of this how long it is being held in a particular phase as if it is being held in a particular state of a Markov chain, right. So, that is the view that we can take to generate an Erlang or to contribute to the alternative view of this Erlang distribution, for which consider the following 3 state continuous time Markov chain, and here 1 and 2 are 2 states which are non-absorbing, and 3 is the state which is an absorbing state. So, you make one state as an absorbing state, and there are some number of states that will be non-absorbing states, and the associated Q matrix, if the rates are mu and mu, meaning the rate transition of moving from 1 to 2 is mu. So, that means what? If it starts at 1, right, or 2, wherever it is there currently, it spends an exponential amount of time with parameter mu, and then it moves out. When it moves out, it always moves to this the next state in this order. So, it is going to 3, if it is in 2, it will be going to 2 if it is in 1. And if I look at the Q matrix or the generator matrix for this Markov chain, then this is what you will get, right, this is what you will get. Now, suppose if you assume that the process starts in state 1, right, that means the initial distribution is 1 0 0, and you define T to be the time of absorption of this Markov chain in state 3. Then what we can see is that T follows an E2 distribution with mean 2 by mu, or in general in this particular case it is basically a simple gamma distribution with mean 2 by mu, and another parameter is S2, right. Because if you look at in state 1, the sojourn time in state 1 or the holding times are the time the process spends in that particular state in state 1 or in state 2, they are exponential with mean 1 by mu each. So, suppose now we are assuming that initially it starts at state 1. So, that means that it spends an exponential amount of time in the state 1, and then it moves to an state 2, and again it spends an exponential amount of time in state 2, and then it moves to state 3, right. So, here it spends an exponential amount of time, here it spends an exponential amount of time. So, starting from here, the time it gets absorbed into this 3 is sum of these 2 exponentials, right, and the sum of these 2 exponentials is what then E2 distribution, right. So, this is an alternative view of this one, but here you know, if we have to stick to our definition of exponential, then we ideally have to write, take the rates as 2 mu here, right. So, the matrix will have instead of mu 2 mu everywhere, and then this E2 distribution will be having then mean as 1 by mu, right. So, that is what it is, but just to illustrate that you should not get fixated with that idea alone, that we are given in general here. Even if it is mu, you can still call it Erlang, no problem, but with the mean is different. You have to be careful what is its mean and its variance or covariance, coefficient of variation accordingly, right. Alright, this is a deviation, this is not the common one. The normal one will have 2 mu here, 2 mu here, so all the rates will be 2 mu's, and then so this is because we want to illustrate in terms of CTMC. So, let us not have 2 mu, instead of that we could have mu itself to illustrate this purpose, right. So, this is what is an Erlang distribution. So, here what we have done is we have used that the phase is exponential. We are using the fact that in a Markov chain the residence time or the holding time or sojourn time of the process in a particular state is exponential. So, we are using that to construct a Markov chain with an absorbing state and the remaining as non-absorbing states, right. They will not be recurrent in any case, right, because the chain has to ultimately should get absorbed into this absorbing state. So, we construct a Markov chain of that form and with the corresponding Q matrix and with an appropriate initial distribution. Suppose if the initial distribution, if you vary, you will get different distribution. Okay, you can make using that, right. But this Erlang will have always this 1 0 0 as the initial distribution and this matrix as the Q matrix of the Markov chain. So, the Q and P can be used appropriately to generate distribution. So, for this particular Q, for this particular P, you will get the Erlang distribution. Now, so basic idea of generating a phase type distribution is this, right. What is that? So, the phase type distribution, which is what we want to look at, is defined as the time to absorption in a specified continuous time Markov chain. That is the first part, right. So, you are defining the duration that follows a phase type distribution as the time to absorption in a particular continuous time Markov chain. So, you define an appropriate CTMC. So, now by choosing different CTMCs and by choosing different initial probability distributions, we can construct different phase type distributions. So, these distributions are not exponential in general, but they can be analyzed using the CTMC theory. That is the advantage, by taking or by appealing to the properties of the exponential distribution, which helps us a lot in analyzing the models analytically, right. So, this is the idea, that a phase type distribution is defined as the one corresponding to time to absorption in a specified Markov chain, and by picking these Markov chains and by picking even with the initial distributions, we can construct different phase type distributions. Okay. That is the basic idea of phase type distributions. Now, let us see how we can make a different general one to generate what we call as hyper exponential distribution. Okay, how do we generate a hyper exponential distribution? We know hyper exponential distribution is really mixture of two exponential distribution, two independent exponentials with parameters say mu1 and mu2, for example. Okay. So, that same thing can be represented as one that is arising out of this Markov chain. So, this Markov chain also has the states 1, 2 and 3, but the rates here from moving from 1 to 3 is mu1 and 2 to 3 is mu2, and 3 is an absorbing state, 1 and 2 are transient states or non-absorbing states, and the corresponding Q matrix would be then of this form, right. So, this dotted line is what you need to remember in mind, because this is how it is going to define something here. Okay. So, this portion is what is the Q corresponding to the non-absorbing states, and this is the rate from non-absorbing to absorbing, and this is the the absorbing state to non-absorbing. Obviously, this has to be equal to 0, otherwise this will not be an absorbing state, and for absorbing state, as you know, the diagonal entry would be 0, right. So, this is what the Q matrix that you will have here. So, this is the Q matrix. Now, let the chain start in state 1 with probability Q and in state 2 with probability 1 minus Q, right. We will always assume that the chain will not start in here, then you are not going to get anything, right. The time is 0. If it has to be found represented as the time to absorption, it has to start in a non-absorbing state. So, that will be with some probability. So, that is why many a time this third quantity may not be given, this will, and the non-absorbing states probabilities, starting probabilities, if you sum, they will give you a proper distribution. So, this P of 0 would be this in this particular case. Now, then T, the time to absorption, follows a hyper exponential distribution, because this is a mixture of two independent exponential. So, because it will start with probability Q, the time to absorption is exponential with parameter mu1, and with probability 1 minus Q, the time to absorption is exponential with parameter 1 by mu2, right, and that is precisely your hyper exponential distribution, and this hyper exponential distribution will be denoted by this notation h suffix k, hyper exponential, the number of in this case you can think this as the phases, right. So, this is, you are representing a hyper exponential in terms of exponential, right. So, this is what we have here, right. So, this is another example or another using this Markov chain viewpoint, that how one can generate using exponential. But so far what we have seen, these are two simple examples. Like now what we will do, we will give a formal approach as to how one can determine the distribution of time to absorption in a general CTMC. So, to illustrate that, we take this particular hyper exponential example itself, okay, and we will explain that process. Okay. Now, suppose if I call this as the hyper exponential Markov chain just for the sake of illustration, then this the forward Kolmogorov equation for this Markov chain CTMC can be given by this P dash equal to Pt times Q, and if you write this explicitly, then this is what you will get as the forward Kolmogorov equations, right. So, we need to solve this equation to get P1t, P2t and P3t and so on, right, to get the solution. So, to do that we need initial distribution, and initial distribution we know that P10 is Q and P20 is 1 minus Q and P30 is obviously 0. Now, if I take this one, this is just a simple linear differential equation, and this can be easily solved to obtain this using the fact that P1 of 0 is Q, right. Now, similarly, the second one will give you this. Now, if you simply substitute into the third, then mu1 times Q e to the power minus mu1 t plus mu2 times 1 minus Q times e to the power minus mu2 t. Okay. Note that by definition P3t, what is this P3t is that the probability that you find the process in state 3 by at time t, right, and you are starting at somewhere else. So, this P3t is basically the CDF of t, right. This gives you what is the probability that the time or the Markov chain get absorbed into state 3 before on or before time t, right. That is what this probability would give you. And this, if this is the CDF, then its derivative will give me the PDF, and hence this is a PDF, and this is the PDF of a H2 distribution, hyper exponential distribution, as you expected, right, because this is Q times an exponential plus 1 minus Q times another exponential. So, this is the mixture of two exponential with the mixing quantity being Q and 1 minus Q. So, this is a two term hyper exponential distribution which we denote it by H2. So, in queuing literature that you will find this H notation being used frequently, much like this E notation for Erlang distribution. So, that means always a hyper exponential distribution which is a mixture of exponential distribution which can be modeled through this kind of Markov chain, and this is what you have here, right. Now, alternatively, like here in this particular case, this is what is the case that we have. So, we have this forward Kolmogorov equations from where you solve and to get this absorb quantity which is corresponding to the absorbing state to get the time to absorption of this. So, that is what So, which means that basically what you are doing, you are looking at the non-absorbing states here which is 1 and 2, and you have this system of equations that you are solving corresponding to the probabilities Q and 1 minus Q, and once we have these expressions for P1 and P2, I can simply substitute into this the absorbing states the Kolmogorov equation to get the density of the time to absorption of this Markov chain, right. That is what you are seeing it here. Now, if you adapt this, if you write this generically, this is what you will have. Now, let us call this P tilde to be, right, from this P you leave out only the absorbing state and call the remaining ones as P tilde of t corresponding to the non-absorbing states, and let Q tilde be the corresponding matrix. What do you mean by corresponding matrix? The corresponding matrix means this matrix, that is what we said, that this the dotted lines divides this. Now, once I have this matrix, then this mu1 mu2 can be given by the negative of this matrix multiplied by the vector of 1s will give me this vector automatically, right, and this is a 0 vector and this is a 0 entry. So, this is automatically determined all three. So, if I give this part, then I know what is this last column which is corresponding to the absorbing state, which is basically here you can write it as okay. So, you will write it here. Okay. So, in this case, so my Q would be right, q tilde, and this is minus q tilde e, and this is 0 vector, and this is 0 entry, right. So, this is what the quantities that we have already seen it expressing it in the other case, right. So, this is what would be the q. So, this is the corresponding q, meaning this portion is what you call q, and the corresponding to that, if you write, then this is what would be the equations, because that is what you will have, because this is 0 here. So, this is not going to contribute anything to this particular equations. So, the solution to this matrix system of differential equations is given by this, much like as if it is scalar differential equation case, right. You will have this expression where my initial condition is this, which is a proper probability distribution, right, where this is what is called this matrix exponential, because now q tilde is matrix. So, this matrix exponential like the ordinary exponential can be given in terms of this series expansions. Of course, you have to worry about their convergence and so on. So, in this particular case, what you will be seeing is that this is 1, this identity matrix plus q tilde times t. Oh, sorry, there is a t here missing, okay, and this is this second terms, third terms and so on, and if I sum, I will end up with this. So, this is what is the matrix exponential corresponding to this particular quantity. If I have more complex q, then obviously I need to worry about obtaining this in a more compact way, but of course, in the matrix theory there are well established procedures to get to this, okay, fine. So, once I get this, I can substitute here with this initial condition given by this, then I can get. Now, if this is my e to the power qt, I substitute here my this vector is q into 1 minus q. So, q into 1 minus q multiplied by this. So, what is going to give you q times this, right, and 1 minus q times this, that is what your p1 of t, p2 of t, even earlier you had obtained q times this and 1 minus qt, this is what you have obtained, right. This is what is your p. So, p1, p2 that you have obtained here in this particular case. Now, which is the same one which we have as we have obtained earlier. Now, from there you can substitute into this equation to obtain the density of this. So, in general, a phase type distribution is described through alpha and q tilde, where q tilde is as this, and this is what would be called as this alpha, as in this particular case is this vector is what will be called as alpha, right, where this alpha is equal to this and q tilde is basically as we have given corresponding to the non-observing states, and this will be denoted by this notation pH of alpha and q tilde. Sometimes q tilde, even if it is not there, some q is given or p is given or anything is given, then it is the same, that this corresponding to this non-observing. So, a pH distribution in the description, when I have this alpha and this matrix, that means this is the initial probability vector and this is the matrix or the Q matrix entries corresponding to the non-observing states is what is given. Now, you can apply this procedure to an appropriate E2 distribution case and obtain this. Remember, now in this particular case we are now putting it as if this is a proper the usual E2 distribution, where the mean is 1 by mu and the number of phases is k, which means each of this phase will have the rate as k mu, and hence here if it is, it will be 2 mu, that is what is the case. So, you can try this again using this process whatever we have described just now here. Okay. Now, let us use this to describe to get to know the another distribution which is called as hypo exponential distribution. What is that? Which we have already seen to be sum of independent exponential. Again, you are expressing this distribution in terms of exponential, right. Now, to do this you follow this continuous time Markov chain, where mu1 not equal to mu2 and the system starts in state 1, right. So, much like Erlang, but there is a difference that this is not mu1 is not equal to mu2 here. Okay. So, it spends an exponential amount of time here and with parameter mu1, and again it spends an exponential amount of time here with parameter mu2 before it gets absorbed into state 3. So, the matrix will be of this form with P naught to be equal to the same. Now, this is time to absorption is now the sum of two non-identical exponential random variable, right, and this is not Erlang, since Erlang requires identical exponential, right, which we know. And if you obtain the distribution of this P1 P2 using the approach which we have just described. So, we know what is this Q tilde, and we know 1 0 as my alpha, or P tilde of 0. So, I can just get what is my e to the power qt. So, I have to obtain now this matrix exponential. This is the main point here, the obtaining the matrix exponential, right. Now, if I obtain and if I obtain P1 and P2, I can obtain to be these quantities, right. P1 will be a simple exponential, but P2 would be this, right, you can see. Therefore, right, this P3 dash of t, which is mu2 times P2t, which will be given by this. We have seen earlier also this expression whenever we talked about sum of two non-identical exponentials. So, this is how you can obtain here, right. So, we now have a method for obtaining more general distributions and still use Markovian methods, and this can be of great help in many situations, right. So, this is the continuous time version, but again you have a what we call as a discrete phase type distributions to handle the discrete distribution that may arise, right. But since mainly we are concerning about continuous distribution, we did not mention, but that is what is the case that you may have here. So, this is now, even if it is, for example, if I change the initial distribution to be something else, right, instead of 1 0 I can make say half half suppose, then you will get another distribution. Or the behavior, like you could have either go here or it can go here with certain rates. If you think all these forms, that you will get different CTMCs, and it can give you different distributions which can quite get approximated in terms of phases, right. So, that is what is the advantage of using this phase type distributions, that one can still be within the Markovian framework when you are trying to analyze this distribution. What we will do is that we are not going to deal with phase type distribution, because the theory becomes much more complex, though it mirrors the scalar quantities, but now you have to handle all matrices, right. So, what is called as quasi-birthed processes, MG1 type or GM1 type model, these are, you can have matrix versions of that, but they will be very difficult to handle, which we are not going to do it in this introductory course. So, what we will do is that we will now take up, once we have this idea, right, this idea is important, that Erlangian. Now, you can easily generalize this Erlangian analysis that we are doing it, how we are doing this Erlangian queues to say hyper exponential, or Coxian or phase type distributions in a similar way, right, but the complexity might increase, but in a similar way this can be handled. That is what you need to understand. So, to illustrate that, what we will pick it up is that we will take up only the Erlangian case, and then we will talk about how one can analyze this Erlangian case, queues with Erlang distribution, which will form then the general then the exponential, and we already know Erlang itself can give lot of flexibility in modeling when you are trying to use the general distributions for this, okay, which we will take it up later. Thank you, bye.